Using more than 1 million GPU hours on the Zhongzhei French supercomputer, researchers from around the world created Bloom, a large language model with 176 billion parameters trained on 59 languages that is open access. How did they do it? Perhaps more interestingly, why did they do it? This video describes the motivation behind the BigScience initiative, the training data, and the Bloom model that was ultimately released. Bloom is described in a paper released on arXiv in November 2022 by Scao and almost 400 other authors as part of the BigScience Workshop. Let's start with the motivation. Pre-trained large language models now play a key role in NLP because they are able to adapt to tasks with less labeled data than models without pre-training. The first recipe to use these models to achieve major breakthroughs was to combine pre-training with fine-tuning on a relatively small amount of task-specific data, highlighted in influential works like Elmo, ULMFit, GPT, and BERT. A second, potentially even more practical recipe then emerged, of pre-training followed by direct zero-shot application of the models, as demonstrated in works such as GPT-2 and GPT-3. A key empirical observation that has influenced the development of these models is that increasing model scale, along with other factors, brings predictable gains in performance, a finding that has been highlighted in a range of systematic scaling law studies. Linked to this push to greater scale, which makes capital a limiting factor on performance, training larger language models has become unaffordable for all but the most well-resourced organizations. Moreover, until recently, most large language models were not publicly released, so few researchers have been able to participate and shape how these models evolve. It's also interesting to note that large language models to date have been mostly English, with a few exceptions such as Pangu Alpha for Chinese and Hyperclover for Korean, with limited support for other languages. The Bloom model released in this work aims to address these challenges. Bloom is short for Big Science, Large Open Science, Open Access Multilingual Language Model. It's a 176 billion parameter language model that was trained on 46 natural languages and 13 coding languages, using compute funded by a French public grant to use the Zhongzhei supercomputer. The goals of the project were to both release a strong multilingual large language model and to document the coordinated process involved in its development. Before looping into Bloom, we'll do a brief review of some background ideas. This work focuses on language modeling, which is the task of modeling the probability of token sequences. Here, tokens are some units of text. They can be a word, subword, character, byte, or indeed any other form of suitable text representation. This work, and many others, aim to model token sequences autoregressively, which is to say that in order to model the joint probability of a sequence X, which comprises T items, the joint probability is decomposed into a set of conditional probabilities, in each case modeling the probability of the next token by conditioning on the tokens that preceded it. To tackle this modeling problem, some of the earliest work focused on n-grams, as studied in Shannon's seminal theory of communication. However, n-gram models have several issues. Their size scales poorly, in fact exponentially, in the value of n, and they don't have an obvious way to assign non-zero probabilities to unseen n-grams without additional tricks. A different line of work has pursued the use of neural networks to estimate the probability of the next token. This idea was studied in the 90s in work by Mikalainen et al. And Schmidt-Huber et al. And gained traction with the 2000 work of Benjo et al. Over time, the architectures used for language modeling with neural networks have evolved from focusing on feed-forward networks on fixed window sizes to RNNs, and more recently to transformers. As the researchers have evolved, there has also been research on transfer learning, which involves pre-training on a general corpus and then fine-tuning on a downstream task of interest. In this vein, there was particularly influential early work on word vectors that adopted a pre-training phase to produce embeddings, perhaps best exemplified by word2vec. However, there has been a transition towards an alternative approach that pre-trains and fine-tunes the entire network, as studied in the NLP almost from scratch framework of Colobert et al. In this latter vein, the particular benefits of pre-training transformers for transfer learning were highlighted by GPT and BERT. Later work has shown that zero-shot and few-shot abilities emerge from these models as they increase in scale, a finding that is particularly associated with GPT-2 and GPT-3, but has also been reported in other work. A number of social issues have been identified with large language model development to date. These include the environmental impact of training, an issue highlighted by Strubel et al., among others. Another consideration is that the design choices of pervasive technologies shape the lives of people in a manner that is akin to regulation, but without equivalent consultation, a theme considered by Winner in his influential works studying the political aspects of technological process. In light of this, it's particularly noteworthy that development of large language models has been concentrated in corporations, with Eluther AI representing a rare exception as the only non-corporate entity outside of China developing these models prior to the BigScience Workshop. The Bloom model was developed by BigScience, an open research collaboration with the aim of publicly sharing a large language model. Initially, the collaboration included Hugging Face and members of the French NLP community, after receiving some ambitious funding support for compute from GENCI, the French public high-performance computing agency. In the end, the project grew to include over 1,200 registered participants. These included individuals with backgrounds in machine learning and computer science, but also in stats, law, linguistics, philosophy, and sociocultural anthropology, among other domains. Ultimately, hundreds of researchers contributed to project artifacts, with a total of 38 countries represented. The largest number of participants came from the US, but there was coverage of other geographic regions too. The project was organised around a set of working groups, each of which had a chair responsible for organising work to tackle some aspect of the project. The participants were encouraged to join multiple working groups to help share information. The 30 working groups that ultimately emerged spanned many areas. There were working groups on data, focused on data preparation, sourcing, governance, tooling, and analysis. There were working groups on modelling, focused on tokenization, metadata, multilinguality, architecture, retrieval, and prompting. On various aspects of evaluation, hackathon organization, extrinsic, intrinsic, few-shot, interpretability, bias fairness, and multilinguality. Then there were cross-area working groups on organization, engineering, collaborations, and ethics and legal, on the specific domains of biomedical and historical text. Finally, there were working groups on external impact, with focuses on model sharing, socials, media, model cards, environmental impact, and the Bloom Book. As part of the ethical considerations that went into the project, there was a collaboratively designed ethical charter that sought to recognize and begin addressing the social limitations associated with large language models within the BigScience Workshop, as well as new research on non-US regulation relating to NLP. The core values focused on by the charter were inclusivity and diversity, openness and reproducibility, and responsibility. We now turn to the training dataset, a motivation for the approach taken in this work, which starts with the observation that data work is undervalued. There is a general sense that everyone wants to do the model work, not the data work, as highlighted by Sam Basivan et al.'s work on data cascades. The focus in constructing large language model data to date has broadly been to use heuristics to get as much high-quality data as possible. Here, high quality is used to refer to data that maximizes performance on downstream tasks, possibly minus content judged to be offensive by the data collector. This approach yields terabytes of data relatively efficiently, but compounds biases in the source data. For example, it was found by Dodge et al. In an analysis of C4 that block lists for pornographic terms can disproportionately filter out LGBTQ+, African American English, and Hispanic-aligned English text. A recent study by Johnson et al. Explored the complex question of the values expressed by GPT-3, finding that model outputs tend to align with reported dominant US values, and suggesting more broadly that data curation and filtering may play an important role in this. Work by Behane et al. Found that the use of automatic clip filtering can exacerbate bias in multimodal dataset creation. In general, abstractive approaches to data curation tend to produce results that are difficult to document and govern, since data provenance is often lost along the way. One potential route to address this is to prioritize compilations of documented data sources, an approach taken with the piled dataset, for example. In the BigScience Workshop, the aim was to prioritize human involvement, local expertise, and language expertise in the curation and documentation processes. We next turn to the question of data governance. As datasets continue to grow in scale to train large language models, we need new systems and ways to account for the interests of the developers, data subjects, and rights holders. One aim of BigScience was to address these needs by combining technical, legal, and sociological expertise. There were two goals for the governance efforts as part of the workshop, operating over different timescales. The first was to explore structures for long-term international governance of data. Work in this direction is reported in Jernite et al., who describe a model for data governance in which a data stewardship organization works together with data holders and data rights holders. The second was to provide concrete recommendations for BigScience project data that drew on lessons from this effort, given that it was not possible to fully set up an international organization in the short time span of the project. These included seeking explicit permission from specific data providers within the BigScience context where possible, keeping data sources separate until final pre-processing to help with traceability, and providing a composite release of data that aimed to support reproducibility while also respecting the source-dependent needs of the different datasets. This involved providing tools to inspect and visualize data, including online demos to enable analysis of the full corpus, and also making 223 of the 498 datasets that form the corpus available for direct use. This subset was the subset deemed appropriate for direct distribution after accounting for licensing, privacy risk, and agreements with data custodians. Finally, since future research to analyze Bloom may require access to the full corpus, a sign-up form is provided for this use case. The dataset that Bloom was ultimately trained on is called the Responsible Open Science Open Collaboration Text Sources, or ROOTS dataset. This contains 1.61 terabytes of text, 46 natural languages, and 13 coding languages. To give an idea of composition, here is a tree map of the content, where the area is proportional to the number of bytes in each subset. We see that much of the data comes from Indo-European and Sino-Tibetan language family. Additionally, there are 18 gigabytes of Indonesian data and 0.4 gigabytes of data from the Niger-Congo language family. We can also examine a waffle plot of the 13 coding languages, where each square corresponds to approximately 30,000 files. The data is formed of Java, PHP, C++, Python, JavaScript, C#, Ruby, Lua, TypeScript, Go, C, Scala, and Rust. The strategy for determining dataset composition was driven by two goals in natural tension. First, to build a large language model that is accessible to as many people as possible globally. Second, to limit the dataset to languages where the project has sufficient expertise to curate and document the data. The approach taken was to start from the 8 largest languages in terms of number of speakers, proactively inviting fluent speakers of these languages to contribute. Following the recommendations of recent works, this was expanded to include Niger-Congo languages and Indic languages. The data was further expanded to include languages with 3 or more fluent speakers amongst the workshop participants, who could commit to supporting the data process in order to avoid common issues that occur from a lack of language expertise, as flagged by Kreutzer et al. In order to select sources, a list was curated in the form of the BigScience catalog via hackathons with different communities, as described by Macmillan-Major et al. This was extended with a collection of language-specific sources, as well as websites identified by participants in their local language that could be extracted from a common crawl snapshot. Code was collected from GitHub via BigQuery, mimicking the languages used by AlphaCode. Finally, to get enough data to train Bloom and to avoid straying too much from prior work, Oscar was used as a dataset source, specifically the February 2021 snapshot of Common Crawl. This ultimately formed 38% of the ROOTS corpus. The dataset pipeline involves multiple stages. For crowdsourced datasets, the sourcing process first gathered from identified datasets and collections, pseudo-called data, and GitHub code. This data fed into a manual merging and source deduplication effort. The Common Crawl-based dataset started from the Oscar February 2021 snapshot. Both were then pre-processed by a semi-automatic cleaning, filtering, and deduplication stage. The key quality filtering metric employed was whether the text was written by humans for humans, rather than scoring it by its content. An additional step of removing personal identifiable information using regex searches was applied to the Oscar data, which was thought to have the highest privacy risk. The resulting data was then collected into the final data store. A range of recent work has investigated multitask prompted fine-tuning, also known as instruction fine-tuning, which involves fine-tuning a language model on a set of tasks that are specified via prompts in natural language. As part of the BigScience effort, a method called T0 was trained on a subset of the public pool of prompts, or P3, a set of more than 2,000 prompts curated through hackathons as part of BigScience. P3 itself was collected with PromptSource, an open source tool that was also developed in the BigScience Workshop. A core finding from T0, corroborated by other recent work, is that large language models fine-tuned on multitask mixtures of prompted datasets can generalize to zero-shot tasks. In order to apply this to the multilingual Bloom model, P3 was extended to include non-English datasets and additional tasks such as translation. The result was the XP3 dataset, containing prompts spanning 86 datasets, 46 languages, and 16 tasks. An additional variant of the dataset that machine translated the English prompts into the language of the underlying data was also created, known as XP3MT. We can visualize the distribution of XP3 by plotting language on the x-axis and percentage of corpus on the y-axis. Here is the result, with XP3 in maroon and ROOTS in dark blue. We see that they follow a related language distribution. At the larger end, XP3 is 39% English, while ROOTS is 30% English, while at the tail end are less represented languages like Tree. We now turn to the model architecture. The design methodology starts with the noting that an exhaustive exploration of architecture design is infeasible, given the size of the design space. One option to avoid this is to simply adopt an existing large language model architecture with a good track record. As noted by Narang et al., there has been lots of work to improve transformers that has seen little adoption, in part because modifications to transformers don't seem to generalize very well. Still, adopting proposals from the community, if effective, could bring gains. The approach taken with BigScience was to adopt a middle ground. focusing on models that have been shown to scale well, while ablating components and hyperparameters to make best use of the compute budget on Zhongzhe. The ablations focused on zero-shot generalization, which has the benefit of being more practical than fine-tuning, particularly with large language models. The evaluations used for ablations are the 29 tasks in the Eleuther AI evaluation harness, and the 9 tasks in the T0 evaluation set, which has some overlap but different prompts. The models used for the ablations were 6.7 billion parameters for the study of the pre-training objective, as described in Wang et al., and 1.3 billion parameters for the study of positional embeddings, activations, and layer norm, as described in Scao et al. One caveat to note here is that a recent study of quantization for large language models by Detmers et al. Identified a phase transition in which outlier features begin to systematically occur in models with 6.7 billion parameters and above. So it's possible that the results of studies at 1.3 billion parameters may not generalize to the largest Bloom model. Architectures considered out of scope for the project included sparsely gated mixture of experts language models, such as those studied in Shazir et al., given the lack of GPU code for training these models at large scale. Also out of scope were state space models, as studied by Gu et al., whose results at the start of the project were not competitive for language modeling. More recently, there have been strong large-scale results for mixture of experts such as trillion-parameter switch transformers, and promising results for state space models at smaller scale, with the techniques introduced in H3, so these approaches could be considered for future work. To choose a good configuration, the project conducted a study of architecture choices, comparing encoder-decoder and decoder-only models and their effectiveness with different losses, specifically causal, prefix, and masked language modeling. The results, reported in Wang et al., find that immediately after pre-training, causal decoder-only models work best, which matches the approach of current state-of-the-art language models and suggests that these models are following a reasonable formula. It was also found that causal decoder-only models can be efficiently adapted to a non-causal architecture and objective by changing the masking pattern and continuing pre-training, a result corroborated and extended in the recent work of Tay et al. After various studies, 2 architectural changes to a standard causal decoder-only model were ultimately adopted. The first was to use alibi position embeddings. This technique, short for attention with linear biases, works by attenuating attention scores based on the distance between queries and keys, by adding a simple bias term to each attention score. The second change was to add layer norm directly after the embedding, following the bits and bytes library, given the finding that this typically improves training stability at the cost of harming zero-shot generalization. One note here, later work such as GLM 130B highlighted the role of float 16 in causing loss spikes. Since Bloom ultimately used bfloat 16 for training, which has a higher dynamic range, it's possible that the embedding layer norm may not have been needed. Putting this all together, token sequences are embedded and passed through a layer norm. Then, they are fed into 70 decoder blocks, another layer norm, macked back through the embeddings and passed to a softmax. Each decoder block consists of multi-head attention sandwiched between layer norms and an MLP. The multi-head attention itself takes a familiar form, but with alibi mask values added to the key query products. As noted by Mielke et al. In their short history of tokenization, it's common to reuse tokenizers. For example, GPT-3 and OPT both reuse GPT-2's tokenizer, a tokenizer that is trained for the English language. This made sense in the context of these studies to control for factors of variation. However, given the diverse data in roots, reusing this for Bloom may be suboptimal. So, a tokenizer was trained on roots after removing duplicates. Otherwise, it was found that entire URLs are stored as tokens, with sampling that preserved the language ratios of the training dataset. After experimenting with different vocabulary sizes, a vocabulary size of 250k tokens was chosen, or more precisely, 250,680 for efficiency reasons, with 20 tokens spare for future use like redaction placeholders. The tokenizer uses learned byte-level byte pair encoding, which works at the level of bytes rather than characters, in the style of the GPT-2 tokenizer. No normalization was applied to keep the model as general as possible. The pre-tokenization, for those who get their thrills from reading regex, was this, or equivalently, splitting on words, but keeping space and line break sequences that are important for coding languages. Each of these choices was sanity checked by computing the fertility of the tokenizer for various languages. This is the number of subwords produced per word, a metric discussed by Arch in the context of tokenization. The goal was for the Bloom tokenizer to avoid increasing fertility on each language by more than 10% versus some standard monolingual tokenizer baselines. This was assessed on subsets of Universal Dependencies 2.9 and OSCAR. This goal was mostly achieved. There was a 13% increase in fertility for Arabic, but otherwise solid. We now turn to look at some of the engineering behind training Bloom, which took 3.5 months on 384 80GB A100s and amounted to 1,082,990 compute hours on the Zhongzhei cluster. The configuration used 48 nodes for training, with 4 spare for hardware failures, where each node had 8 GPUs and 512GB of RAM. Storage was handled by the GPFS parallel file system, covering a mix of flash and hard drives. Intranode communication used 4 NVLink GPU to GPU interconnects, while internode communication used 4 OmniPath 100 gigabit links per node, arranged in an 8T hypercube global topology. The training framework used for Bloom was Megatron DeepSpeed, which consists of 2 elements. First, Megatron LM, which provides a fast transformer implementation, tensor parallelism, and data loading primitives. Second, DeepSpeed, which provides the zero optimizer, model pipelining, and components for distributed training. 3 kinds of parallelism are used. First, we have data parallelism, which replicates the model across devices in such a way that each replica sees different slices of the data. The replicas get synchronized after each training step. Second, we have tensor parallelism, which splits within individual layers across multiple devices. Third, we have pipeline parallelism, which splits different layers across devices. Taken together, these combine to provide 3D parallelism. Here's the layout of the 384 nodes, arranged into 8 blocks of 12 by 4, where each little box represents a single NVIDIA 80GB A100 GPU. To implement data parallelism, separate batches are fed into the blocks of 48 nodes corresponding to each replica. Let's zoom into the rightmost block of 48 nodes to see how the other kinds of parallelism work. Our batch of data comes in at the bottom. Tensor parallelism works by splitting the parameters of the model within individual layers across GPUs. In this case, we are splitting 4 ways for processing. Pipeline parallelism runs across the 12 GPUs in each block. To help with memory, the 0 stage 1 optimizer is used, which corresponds to sharding optimizer states. This setup ultimately achieves approximately 50% utilization of the GPUs, which is pretty solid. In initial experiments with training a 104 billion parameter model on V100 GPUs, there were training stability issues. The authors believe that this may have arisen from use of the IEEE float16 format. In the final training run, A100s were used, which support bfloat16, which has the same dynamic range as float32, but much lower precision. Mixed precision training was used, combining float32 precision for sensitive operations like gradient accumulation with bfloat16 precision for the others. This approach was found to resolve training instabilities, mirroring the findings of work on the Megatron Turing NLG 530B model. One way to accelerate GPU processing is kernel fusion, which involves executing multiple consecutive operations in a single kernel call, as studied by Wu et al. Bloom training uses several custom fused CUDA kernels from Megatron LM for layer norm and an assortment of combinations of scaling, masking, and softmax. The bias term is also fused with GLU activations via PyTorch JIT. Some of the other challenges tackled in scaling up to 384 GPUs required disabling asynchronous CUDA kernel launches to avoid deadlocks and make debugging a little simpler, and splitting parameter groups to avoid excessive CPU memory allocation. Hardware failures were encountered at a rate of approximately 1 to 2 GPUs per week, which was ultimately not too disruptive, given automatic handling and the use of checkpoints saved every 3 hours. A range of architectures were employed during pre-training, ranging from 559 million parameters up to 176 billion, with model depth and width choices approximately following those used in prior work, such as GPT-3 and OP2, with a few deviations. The roots dataset contains roughly 341 billion tokens, and the plan was to train for an equivalent number of tokens. However, after the publication of Chinchilla and its associated revised scaling laws, the choice was made to train for an extra 25 billion tokens on repeated data. As part of a study on multitask fine-tuning, various Bloom Z models were fine-tuned from Bloom variants. This fine-tuning approximately follows the hyperparameters used in T0 and FLAN, though with some modifications, and it is found that performance plateaus after fine-tuning for 6 billion tokens or fewer. As part of a further study, contrastive fine-tuning is performed with the SGPT bi-encoder recipe on the 1.3 billion and 7.1 billion parameter models. This recipe aims to produce strong text embeddings for multilingual information retrieval and semantic textual similarity. Further benchmarking has found that these models are also well suited to bitext mining, re-ranking, and feature extraction. We next look at carbon footprint, noting that prior studies have focused primarily on the emissions associated with model training, including insightful analyses from works such as Struble et al. And Patterson et al. The approach taken with Bloom was inspired by the life cycle assessment methodology of Klupfer, which aims to account for emissions associated with manufacturing, training, and deployment, as well as other factors that were considered to be beyond the scope of the analysis here. The emissions associated with training were estimated at 81 tons of CO2 equivalent, which breaks down into 11 tons, i.e. 14% for equipment manufacturing, 25 tons, i.e. 30% for power consumption during training, and 45 tons, i.e. 55% for idle consumption of the equipment and computing cluster. We can also compare the power consumption of training Bloom with other models. Here we show model name, number of parameters, power consumption, and CO2 equivalent emission. For the GPT-3 175 billion parameter model, the power consumption was 1,287 megawatt hours, with 502 tons of emissions. The Gopher 280 billion parameter model had power consumption of 1,066 megawatt hours, with 352 tons of emission. The OPT 175 billion parameter model had power consumption of 324 megawatt hours with 70 tons of emissions, while the Bloom 176 billion parameter model had power consumption of 433 megawatt hours with 25 tons of emission. Interestingly, we see that Bloom consumes more power than OPT, but produces far fewer emissions. That's because Zhongzhei is largely powered by nuclear energy. Note that the accounting methods here are not standardized, and the values in italics are estimates, so these figures should be viewed as highly approximate. When considering training emissions versus those of evaluation and intermediate experiments, it is estimated that the final Bloom training one represents 37% of overall emissions, which is a bit lower than the 50% estimate made by the authors of the OPT study. To explore the emissions associated with real-time deployment, a Bloom API was hosted on a GCP instance with 16 GPUs in US Central 1. Which resulted in approximately 20 kilograms of CO2 equivalent per day. This is, of course, not representative of all use cases, but provides a point of reference. As part of the release process for Bloom to support community use, Bloom is accompanied by a model card in the form introduced by Mitchell et al., which describes technical specifications, training details, intended uses, out-of-scope uses, and limitations. For licensing, the project aimed to strike a balance between full unrestricted open access and behavioral use clauses of the kind described by Contractor et al. The latter clauses are used in the family of licenses known as Responsible AI Licenses, or Rails. The Rail license used for Bloom separates the licensing of the source code and the model. The source code has a standard Apache 2 license. The model has 13 behavioral use restrictions, which are based on the model card and the BigScience ethical charter. It also has definitions for use and derived works, which include explicit mention of prompting, fine-tuning, distillation, and use of logics and probability distributions. There has been some extra community discussion around Rail, which may be of interest. An overview of the rationale behind the licensing approach can be found in a blog post by Carlos Munoz Ferrandis. For an alternative perspective, a critique of Rail has been shared in a video by Yannick Kilcher, which can be found on YouTube. To evaluate Bloom, it is compared to various large language models on zero-shot tasks, one-shot tasks, and multitask fine-tuning. Further results are reported on the Holistic Evaluation of Language Models, or HELM Benchmark, and multilingual probing is used for analysis. The prompts themselves are crowdsourced with the prompt source tool developed as part of the workshop. Multiple prompts are generated per task, and a peer review process was used to check for artifacts and consistency. To implement the evaluations themselves, the Eleuther AI language model evaluation harness is extended by integrating prompt source. The resulting prompted language model evaluation harness used in experiments is open sourced. In terms of datasets, experiments are conducted on SuperGLUE, specifically on a subset of tasks that have relatively low compute requirements, on machine translation, specifically WMT14 data spanning English, French, and Hindi, Flores 101 data, and Diabla data, and on summarisation, focusing on the Wikilingua dataset, and in particular, the 9 languages that were among those targeted in the BigScience project. The baselines compared to include MGPT, a GPT-like model trained on 60 languages, GPT-Neo, GPT-J6B, and GPT-Neo-X trained on the pile, T0, OPT, XGLM, M2M, Alexa-TM, MTK Instruct, Codex, and GPT-FR. We first turn to SuperGLUE zero-shot performance, looking at the broad coverage and gender bias diagnostic tasks, Boolean questions, commitment bank, wording context, and the Winograd schema challenge. The different colors represent MGPT, GPTJ, T0, OPT, and Bloom. Different dots represent different prompts. The dashed horizontal line indicates random guessing performance. On the entailment tasks of Boolean questions and commitment bank, performance is reasonably above chance. But on other tasks such as wording context and the Winograd schema challenge, performance for all models is near random. One outlier is T0, which has been instruction fine-tuned and is consistently stronger. We can also look at one-shot SuperGLUE performance on the same subset of benchmarks. There is a slight reduction in variance across prompts, but we see similar overall trends, with all models still struggling to make headway on the latter two tasks. We turn next to machine translation benchmarks, starting with a zero-shot evaluation of WMT14 with Bloom. We'll examine results using a range of different prompts for translating English to French, French to English, English to Hindi, and Hindi to English. In each case, both zero-shot and one-shot evaluations are conducted. Here are the results. A first observation is that there can be major variations across prompts, with notably poor performance with the GPT-3 and XGLM prompts. However, we also see that Bloom can attain reasonable one-shot performance when given the right prompt. We next look at Diabla, evaluated zero-shot. Diabla is an informal dialogue dataset. Results are reported from English to French and French to English for T0, MGPT, and Bloom for 2 prompts. In terms of results, we find that none of the methods are able to translate from English to French, while T0 can translate from French to English a little. Broadly, the results fall into the performance not great category. The key problems observed in the outputs were overgeneration and not producing the correct language, which is clearly not ideal for translation tasks. The next set of machine translation experiments examine one-shot performance on Flores 101. On translation to and from low-resource languages, which is determined according to representation in the Roots training set, we find that performance is reasonable, with Bloom sometimes outperforming the smaller but fully supervised M2M model. In other cases, it is a little weaker, but still reasonable. However, for translation between Swahili and Yoruba, which have fewer than 50k tokens in Roots, the results are very poor. On translation from high to mid-resource language pairs, the results are broadly pretty solid. We also find that results on Romance languages are reasonable, even for Galician, which is not explicitly included in the training set, but has many similarities to other Romance languages like Portuguese. Finally, on high-resource languages, we find that one-shot Bloom performs well relative to XGLM one-shot and comparably to Alexa TM 32-shot. And the smaller M2M supervised baseline. We next look at Wikilingua one-shot summarization scores, comparing Bloom models from 560 million parameters up to 176 billion parameters with the 175 billion parameter OPT model. Different dots correspond to different prompts. The numbers reported here are Rouge 2 scores. Broadly, we observe that Bloom outperforms OPT. Next, we'll walk through the evaluations conducted as part of the HELM Benchmark, which aims to provide a holistic evaluation of language models across a broad range of tasks and metrics. We begin by examining accuracy, where higher is better. Each model is scored on its win rate against all other models across all scenarios. Here, Bloom falls behind the leading monolingual models considered in the benchmark like DaVinci V2, Turing NLG V2, Anthropic V4 S3, and OPT. On calibration error, where lower is better, Bloom is somewhat poor, but on robustness, where higher is better, it ranks reasonably well. On fairness, where higher is better, Bloom is above average. On bias, where lower is better, Bloom is roughly average. Finally, on toxicity, where lower is better, Bloom is more toxic than average. Next, we look at the influence of multilingual multitask fine-tuning on zero-shot performance across various tasks, starting with zero-shot natural language inference. Here, the colors correspond to XGLM, Bloom, MTK13B, T011B, BloomZ 7.1b and BloomZ, where BloomZ indicates Bloom with multitask fine-tuning on the XP3 dataset mentioned earlier. In this setting, we find that multilingual multitask fine-tuning brings a boost, a trend that is also reflected in zero-shot co-reference resolution, as well as other tasks. Other results from this study, not shown here, find that T0 also benefits considerably from multilingual multitask fine-tuning. Next, we look at code generation abilities on the HELM benchmark introduced by the Codex authors, reporting performance with parsec k for k equals 1, k equals 10, and k equals 100, where higher is better. One set of baselines include GPT-Neo and GPT-J models that have been trained on the pile, which contains approximately 11% code. The next baselines include Codex models fine-tuned directly on code. The Bloom models, trained on the roots corpus, of which approximately 13% is code, perform in the same ballpark as the GPT-Neo and GPT-J models, but lag considerably behind Codex. Multilingual multitask fine-tuning does not improve things much here, and in fact hurts performance for the largest model, likely due to the fact that there is limited code completion in the XP3 fine-tuning data. The next experiments examine embedding quality on multilingual tasks across the MTEB benchmark. A range of baselines are compared with two Bloom models that use contrastive fine-tuning with the SGPT approach. For text classification on Massive, we find that the fine-tuned 7.1 billion parameter Bloom model performs strongly across the languages included in roots. However, it's important to note that this model is significantly larger than the baselines in terms of parameters. For semantic textual similarity on STS22, we also observe similar trends, with strong performance for the 7.1 billion parameter model. A number of multilingual probing experiments are conducted to understand which features are represented in the trained models. Here, we look at the results of probing the largest Bloom model for morphosyntactic features with the universal probing framework, plotting language on the x-axis and task category on the y-axis. Here are the results, where darker colors correspond to lower values and lighter colors correspond to higher values. White squares in the plot indicate that the morphosyntactic category is not represented in the language. We observe that task categories like mood and person are generally inferred quite effectively across languages, with moderate performance on numeral type, number, and voice. Performance on other tasks like case is weaker. It is also quite varied, possibly in part due to the fact that the set of case values depends on the language. As part of a preliminary study of biases in the Bloom model, evaluations are conducted on Crow-S pairs and the extended French Crow-S pairs benchmarks. These benchmarks compare minimally different stereotyped and non-stereotyped statements and assess whether the model exhibits a preference for one over the other. Examples could include women can't drive, a gender stereotype, and men can't drive, which is not broadly considered to be a stereotype. For English comparisons, results are plotted for 3 Bloom models and 2 GPT-Neo models. For French comparisons, the same 3 Bloom models are compared with 2 monolingual French GPT models. Broadly, we see that Bloom's overall accuracy is close to 0.5, which suggests that, at least under the characterization of these benchmarks, bias is limited. However, there are some important limitations to these results, and other analyses that can be found in the paper. First, Blodgett et al. Discuss some validity issues with the Crow-S pairs benchmark. These are partially mitigated by the French variant considered here, but nevertheless, construction of effective benchmark for bias remains extremely challenging. Second, while results are promising, the bias examinations do not cover the breadth of possible usage scenarios for Bloom. They would be strengthened by further analyses, particularly those spanning other languages, though this is challenging given the lack of available data for such a task. In the video description, you can find links to code and models, slides, and references. Thank you for your attention.